Although the theoretical application of fusion as an energy source has existed since around the 1960s, practical difficulties have prevented it from being realised. While the principle has been proven in reactors today, it is still not yet commercially viable. The primary complexities for fusion energy are the pressure and temperature required to get nuclei close enough to one another. Fusion reactors cannot, of course, be as massive as the Sun, and so cannot use gravity to create the pressure required. One way of creating this, however, is to use a magnetic confinement chamber. This is a chamber within which strong magnetic fields are set up. These fields prevent charged particles from travelling through, and so can contain a hot plasma of nuclei and electrons. To make up for the reduced pressure, a temperature of around 100 million degrees centigrade, about 10 times hotter than the Sun, is required in terrestrial fusion reactors. The plasma is heated by many processes. Ohmic heating involves inducing a current in the plasma, but gets less effective as the temperature increases due to the higher resistance of the plasma. Magnetic compression heating uses the properties of the magnetic fields to cause the plasma to spiral inwards, increasing its density and energy as it does so. Neutral beam injection heats the plasma by injecting energetic neutral particles to transfer energy to the plasma, and radio frequency heating introduces yet more heat by causing the nuclei to oscillate and collide with one another using a radio frequency source outside of the reacting chamber. The most common fuels used in human-made reactors are deuterium and tritium, which are both heavy isotopes of hydrogen. These fuse to form a helium nucleus and an energetic free neutron, which goes on to pass its energy back into the plasma or into a layer on the reactor chamber wall called a lithium blanket, where it interacts with lithium ions to produce more tritium, thus fueling the plasma naturally.